Hello and welcome to my coursework video for group theory and geometry. Today I will be answering my question, which can be found in part 38 to 44 of the question sheet. In this question we have 7 remaining cases of symmetries where each one is related to a platonic solid. The case that I'll be analysing today is star 332. Firstly, I'd like to point out, if you look in the book, this will be written in purely red text, and this is because the pattern can be generated using only mirrors and reflections. So, the first part of the question asks us to find the corresponding platonic solid to our pattern. So, in our pattern, we have 2 threefold mirror points and we have 1 twofold mirror point. This kind of lends itself towards the tetrahedron. So here I've produced a somewhat uninspiring model of a tetrahedron. It's built with 4 faces, all equilateral triangles, and on one of the faces I've actually started dividing it into its fundamental regions. So if we look at it, we have 6 triangular shapes here, and each one of these would be enough to recreate the pattern over the whole shape. So if we had a pattern in this one, we could use these mirror lines, all of these around the shape, to generate the pattern. So to answer the first question nice and short, our pattern star 332 is related to the tetrahedron, like this. I also have another little one here, which I made in practice. So that's the first part of the question. The next part of the question asks us to draw the fundamental region on the platonic solid, which is done, and we then need to calculate the orbifold Euler characteristic. So fortunately, this is one I made earlier. It's just an enlarged version of the one that I drew over here, on this one, like so. And our mission is to calculate its Euler characteristic. So firstly, it's probably worth recalling the formula. V minus E plus F, where we know that V stands for vertices, E stands for edges, and F stands for faces. So firstly, let's talk about the vertices. This is worth a sixth, this is worth a sixth, and this is worth a quarter. And I'm going to explain why they're not full vertices, given that it kind of does look like a point. So if we look back on our model, if we look at the central point, this point is kind of shared by each of these shapes, so it's not really, you can't really call it a full vertex. Instead, our fundamental region is sharing a sixth of the vertex. We don't want any repeats, and this is generally how we do it. So that's the vertices covered. Next we need to look at the edges. So given that each one of these is a mirror line, we can say that they're each worth a half. So there's 3 halves. And finally, there's 1 face. So if we do the calculation, we have 2 sixths plus a quarter minus 3 halves plus 1. And obviously I've done this in advance, so I know that the answer is 1 over 12. So there's the answer to the second part of the question. The orbifold Euler characteristic is 1 over 12. So the next part says that our Euler characteristic should be equal to 2 over G, where G is the order of the group of symmetries for this pattern. 1 over 12 is not in that form, but if we manipulate it slightly, we can say that 1 over 12 is equivalent to 2 over 24, which seems more realistic to the question. So we can answer the second part and say that the order of G is 24. So the group of symmetries related to star 332 is 24, and it also means that we can take 24 copies of this to generate this, and I think this is quite easy to see. 1, 2, 3, 4, 5, 6 times by 4 is 24. Kind of makes sense, doesn't it? So I think the only thing that we need to conclude with is saying that this group can actually be given by S4, the symmetric group with 4 elements in it. This concludes my video. I think it answers the question. Thank you very much.